this presentation is about design engineering, manufacturing, characterization and applications of textile structural composite material. So, let us first see what is textile structural composites. Textile structural composites are the composite materials reinforced by some textile structures, and they are specially dedicated for load bearing applications. The principal objective of making textile structural composites are: we can utilize textile structures in composite manufacturing so that we can achieve advanced composites, load bearing composites and lightweight composite materials. These are the three basic objectives. Apart from that, there are many other advantages also. Other advantages are utilization of advantage of textile structure in addition to textile material, because we use textile material for several other purposes. For example, they are not subject to corrosion, they are light in weight and many other advantages. But when we talk of using some textile structure, then the basic advantage is structural anisotropy. As you know, in many textile manufacturing, we have option to orient the yarn or predetermined amount of textile material in a preferential direction. So, we achieve textile anisotropy. We have opportunity to develop numerous textile structures in weaving, in knitting, in braiding, in nonwovens. We can also manufacture different shape, different geometry. Some of the examples we will also look into in this lecture. Then the important thing is, we are not going to use any new technology. We will be using the existing manufacturing technology, that is weaving, knitting, braiding, nonwoven, and we will develop different products for this purpose. Another important thing is application of design engineering principles. The composite materials are engineered materials. So, while preparing composite and the reinforcement structure, we can use engineering design principles. We can use different computational facilities, we can use different available computational packages, you can use the CAD system for developing innovative structures, and also we can decide or we can really produce an engineered product in composite manufacturing. The basic motivation to develop textile structural composite is, as you know, textile is not an engineered material, it is a flexible but strong material. So, while developing textile structural composite using textile structures, what we are trying to do is, we are making some effort to transform textile material into an engineering materials, and when we are doing so, we are using a huge quantity of textile fibrous material in composite manufacturing. And since the composites are expensive materials, there is a huge value addition to textile materials. So, by developing textile structural composite, we can use value added products. That means lot of financial benefit to textile industry. Let us have a look to what are various materials available in the world. More than 50,000 materials are known to engineers. In this slide, I have given a very broad classification of different materials, starting from natural materials like wood. Wood is also a composite material, it is a natural composite material. We have some natural fibers in textile like cotton, hemp, flax, sisal, many other natural fibers. Then polymers is another important category of material nowadays, for example, polyethylene, polypropylene, polyamide. Then elastomers like butyl rubber, neoprene, the lycra, that is spandex, which is polyurethane, is very common in textile. Foams, then glass, metals like steel or cast iron, and various types of alloys. Then finally, the advanced material is called composites. Composites produced by using GFRP, CFRP or KFRP methods, and of course, there is another advanced materials nowadays called ceramics. So, these are some of the broad classification of different materials used for different purposes. What is the definition of a composites before we really discuss textile structural composite? Here is a very broad definition of composite. The definition is two or more chemically distinct materials which when combined have improved properties over the individual materials. So, what happens in composites? The constituents retain their identities in the composite. They do not dissolve or otherwise merge completely into each other, although they act in concert. So, individual constituents keep their identity in the finished composite product. These are the examples of composites which are available in the nature. So, composite is nothing new, it is already existing. Like wood consists of cellulose, which is considered as a fibrous material, and the lignin is a natural polymer. So, the fibrous material is reinforcement, lignin is the resin matrix. Similarly, the bones of the animals consist of the collagen, acts like the resin, and mineral crystals as the reinforcement. So, composite is basically a combination of reinforcement and matrix, whether it is natural or it is man-made composite materials. This slide shows the time scale of composite advancements. You can see here, even in 2500 BC, we had the concept of composite. We are using straw and mud bricks. So, it is nothing but a composite material, and you can see the series of developments and the polymeric composites using superfibers came sometimes in 1970. So, if you look all these developments, what you can conclude, the composite manufacturing has gone through a paradigm shift. That means, the journey started with natural composites like wood or bone, then polymer composites, then fiber reinforced composites. Now, we are talking of complex structural composites, in the which context we will be discussing textile structural composites. If you look at the history of the composites, the large scale commercial application of composite materials started during World War II, that is sometimes between 1940 and 1950. The polymer based composites were introduced to industry sometimes in 1960. The textile structural composite concept was first initiated sometimes in 1970s, and subsequently the composite materials became the common engineering material. Today, if you look at different higher end applications as shown here in this slide, the composites are the material of choice for many engineering applications like aerospace, automotives, sports, wind energy, marine, railway, construction, and many other applications. So, the basic fundamental concept of composite manufacturing is we are combining a reinforcement with a matrix. In our case, the reinforcement is a textile structure. So, the reinforcement could be a fiber, could be a yarn, or could be fabric. The matrix could be a polymer, could be ceramics, or even metals. We can classify the composites based on two distinct levels, or we call phases of composite. The first level of classification is usually made with respect to the matrix constituent, also called matrix phase, or it is otherwise called the primary phase. The second phase is reinforcement phase. It is also called the secondary phase. And the third phase, it is nothing but it is the interface between matrix and reinforcement. Let us have a look into matrix phase, that is primary phase. In matrix phase, we have three different types of combination: metal matrix composite, ceramic matrix composite, or organic matrix composite. This organic matrix composite is generally assumed to include two classes of composites, that is polymer matrix composites or carbon matrix composite, commonly referred as carbon-carbon composites. Out of these two components, that is reinforcement and matrix, let us have a look to them independently, individually. So, what is the role of matrix? Matrix is nothing but it is a binder. Matrix surrounds the fibers or the textile structures and protects them against chemical and environmental attack. Fibers in and of themselves are of little use without the presence of a matrix. When we try to see what exactly this matrix does, it has many functions. First, it provides bulk form to the composite material. It holds the embedded phase in place and environmentally protect them. Also, the most important role of matrix is it helps to transfer load to the reinforcement. When we try to analyze what are various functions of this matrix, the matrix material initially binds the fiber together. It provides rigidity and shape to the structure. Matrix isolates the fibers so that individual fibers can act separately. This stops or slows the propagation of a crack. The matrix provides a good surface finish quality and aids in the production of net shape or what we call near net shape parts. How it is really achieved, we will discuss it subsequently. There are some special functions of the matrix. The special functions are: matrix provide protection to the reinforcing fiber against chemical attack and mechanical damage. Depending on the matrix material selected for producing a particular composite, the performance characteristics such as ductility, impact strength or tensile properties etc. are also influenced substantially. For example, a ductile matrix increases the toughness of the structure. Thermoplastic based composites are selected for higher toughness requirements. The failure mode is strongly affected by the type of matrix as well as its compatibility with the fiber. So, it is not only the matrix what we have to look into, whether it is compatible with the reinforcement, which is called selection of a matrix. That means how we select a matrix. What is the criteria to select a matrix for different type of reinforcement material? Matrix must have a lower modulus and greater elongation than the reinforcement, so that the fiber can carry maximum load. This is a fundamental requirement of composite manufacturing. Matrix selection is performed based on chemical, thermal, electrical, flammability, environmental, cost, performance and manufacturing requirement. There are many other requirements, but these are some of the important aspects which we look into while selecting matrix for different types of reinforcement. Then coming to the second phase, that is called reinforcement phase. Usually the reinforcement phase serves to strengthen the composite material, because the majority of the strength as high as 90% of the composite strength can be derived from the reinforcement. Modulus of reinforcement agent is always higher than the matrix phase. Reinforcing phase may be in the form of particle, feelers, fibers or filaments or different textile structures of different shape, different geometry and maybe most complex textile structures nowadays available in the form of 3D textile. Complex 3D structures like solid structures, hollow structures, profile structures, aerodynamic and honeycomb structures are some of the advanced reinforcement structures nowadays are being used to produce most advanced composite material. Subsequently, we will be looking into these structures and how they are really helping to achieve various kinds of mechanical properties. This slide shows different types of reinforced composites. So, I have just included some of the important composite categories. Let us start with the first one, particulate composite. So, this is particulate composite, that means particles are used as reinforcement. The resin could be anything depending on the nature of the reinforcement. The second is filler composites. So, fillers are the reinforcement here. Similarly, we have a random fiber reinforced composites. So, random fiber possible only when the fibers are short. They could be oriented in different direction. Even we can try to orient them in a preferred direction also. Similarly, we have continuous fiber, that is filament reinforced composites, where the filaments are oriented in a particular direction depending on the load bearing requirement. Apart from this, we have a very special category of composite we call laminar composite structures. Here, two or more layers bonded together in an integral piece as shown in this slide. This is a very special kind of composites we call sandwich panels. Here you can see we have a face skin, then there is a core. The core could be a foam or even it could be a honeycomb core. Nowadays, textile 3D honeycomb core is being used, which is a very most advanced textile structural composite. Basically, these foam core or honeycomb core, they helps to achieve high strength to weight ratio or high stiffness to weight ratio. When we try to use honeycomb core composite, there are many other mechanical advantages. For example, high impact strength can be achieved by using honeycomb core. All these textile reinforcement can be used in any of these form, could be a chopped fiber, milled fiber, in particulate or powder form, even it can be milled to nano form, rovings, woven textiles, mats, prepregs, and they mixed with a variety of matrix to make the composites. So, in textile structural composites, we have predominantly two things. One is reinforcement, which is a textile structure added with a resin, which is the matrix, and we use this textile structure reinforcement particularly when we are interested in developing load bearing composite material. What are various goals of the composite manufacturing process in case of a structural composites? Here we try to achieve a consistent product by controlling the fiber thickness, the fiber volume, and the fiber direction, that is orientation with the fibers. What I told earlier, that is structural anisotropy. Apart from this, we look into many other aspects. Some of them are mentioned here. We try to minimize the voids, because voids are the source of flaws or defects in the composites, reduce internal residual stresses, and we try to process in the least costly manner. One thing is very important, which we will discuss subsequently also. Composites are anyway expensive substitution of conventional material. So, while manufacturing composites, we try to minimize the manufacturing cost. The properties of these composites are determined by three factors: the materials used as component phase in the composite, number one. Number two, the geometric shape of the constituents, which results a particular structure of the composite system. And the third is the manner in which the phases interact, that is interface, interaction between the reinforcement and the matrix. This slide can give you a very good idea how the reinforcement structure can be monitored or can be managed. Look at various aspects, what is mentioned in the form concentration, size, shape, distribution, and orientation. So, we can control any of these 5 aspects of the reinforcement. And when I am saying reinforcement, in our case, it is nothing but the textile material in the form of fiber, yarn, roving, fabric, or mat, or complex textile structures like 3D fabrics. Let us discuss only few of these properties and analyze how they really influence the properties of composite materials. Let us first discuss fiber fineness. What we call thinner is stronger. It is a general fundamental of textile material. Actual strength of a material is several magnitudes lower than the theoretical strength due to the inherent flaws in the material. That means, as the fibers become smaller in diameter, the chances of an inherent flaw in the materials are reduced. A steel plate may have strength of 100 ksi, which is equal to 689 megapascal, while a wire made from this steel plate can have a strength about 600 ksi, which is equivalent to 4100 megapascal. That means, thinner is the material, it will be definitely stronger, and this is how the relationship. As the fiber dia increases, the strength falls, which is a textile fundamentals. We can understand it very well. The second aspect is fiber matrix interface as a function of fineness. That means, if the fineness of fiber changes, what happens to the interface? For higher ductility and toughness and better transfer of load from matrix to fiber, composites require larger surface area of the fiber matrix interface. And as we know, for the same volume fraction of fibers in a composite, the area of the fiber matrix interface is inversely proportional to the diameter of the fiber. So, the fiber fineness can be monitored or changed to have different fiber matrix interface, hence the properties of the composite. This is a fiber matrix interface and fiber diameter relationship. For example, if a lamina consisting of n fibers of diameter capital D, the fiber matrix interface area in this lamina is n pi dl. If one replaces the fibers of diameter D by fibers of diameter small d, then the number of fibers, let us say small n, to keep the fiber volume same would be capital N into d upon d square. So, what will be the fiber matrix interface area? So, the fiber matrix interface area is given by this relationship, where you can see the diameter is in denominator. What it implies? For a fixed fiber volume in a given volume of composite, the area of the fiber matrix interface is inversely proportional to the diameter of the fiber. So, it is very interesting that if you want higher fiber matrix interface, that means better interaction between reinforcement and the resin or matrix, one can play with the fiber diameter to have higher area of interface. There are many other fiber parameters which influence or contribute to the mechanical performance of the composite material. Some of them are listed here. For example, length, which we already know in textile basics. Long continuous fibers are easy to orient and process, but short fibers cannot be controlled fully for proper orientation. Long fibers provide more impact resistance, low shrinkage, improved surface finish and dimensional stability. However, short fibers provide higher strength, low cost, easy to work and have fast cycle time fabrication procedures. Similarly, if you look other properties, for example, orientation of the fibers. Orientation of the fibers in a one direction gives very high stiffness and strength, which is very fundamental to textile principles. However, for the same volume of fibers per unit volume of the composite, it cannot match the stiffness and strength of unidirectional composites, which we will discuss subsequently. What happens or what is the importance of orientation when you try to develop a textile structure unidirectional, bidirectional or in multidirectional arrangement. This is very important as far as orientation of the fibers is concerned in composite material. Look at the angle between fiber and the stress, that is loading direction. If you go on increasing this angle, the tensile strength increases. So, one can, using this principle, we can change or regulate the direction of orientation of load bearing fiber constituents to have higher strength in the composite material. What all other factors, fiber factors contribute to the mechanical performance of the composite. One is shape. For example, circular shape is preferred for easy handling and manufacturing, as you know, in spinning process. Hexagonal and square shape provide strength and high packing factor, but do not outweigh the difficulty in handling and processing. So, the shape, in one hand, it facilitates the packing factor, it facilitates the mechanical processing. In other hand, it also influences the mechanical properties. Then type of material. So, our material is fiber. Fibers are generally expected to have high elastic moduli and strength. However, the cost have been key factor. At present, majority of the composites materials use glass fibers because they are the cheapest high performance fibers. We cannot afford to use carbon or some aramid like Kevlar or Nomex for many other routine applications because they are very, very expensive. So, cost of manufacturing, for example, particularly as cost of material, is a key factor to manufacture or to produce composite materials. Carbon fiber, as you know, is very, very expensive. They are used only for special applications like aerospace or maybe Formula 1 car, etc. Or glass fibers, which are the cheaper fibers, they are used for some other purposes where the life of the material we do not want to use for a long time. Apart from fiber and the matrix, what other factors influence the mechanical properties? As I have already told, the factor is fiber matrix interface. How the fiber matrix interface influence the mechanical properties? Basically, it determines how well the matrix transfers the load to the fiber, because it is one of the most important properties of the matrix or requirement of the matrix. Then other one is the chemical, mechanical and reaction bonding may form the interface. So, interface between fiber and matrix is very, very important to regulate the mechanical properties of the composite material. Some fibers bond naturally to the matrix and or coupling agents are added to form a chemical bond. The natural roughness or etching of the fiber surface cause interlocking called mechanical bond. Reaction bonding occurs when atoms or molecules of the fibers and the matrix diffuse into each other at the interface. As you can see here in this ACM image, the interdiffusion creates a distinct interfacial layer called the interface with different properties from that of the fiber or the matrix. Although interfacial layers helps to form a bond, it also forms micro cracks in the fiber which reduce the strength of the fiber and thus that of the composite, because the fiber, the reinforcement could be responsible to as high as 90% of the total composite strength. Weak or cracked interface, as you can see here in this slide, can cause failure in composites and reduce the properties influenced by the matrix. They also allow environmental hazards such as hot gases and moisture to attack the fibers. They can penetrate through the structures and influence the mechanical properties or degradation of the structure. What really happens? What is the mechanism behind this? The main reasons for crack development is, it is because of mainly due to the difference in Poisson's ratio, those of the fibers and the matrix. The VF, what is show here, the Poisson's ratio of the fiber, and the VM, the Poisson's ratio of the matrix. If the Poisson's ratio of the fiber is greater than the Poisson's ratio of the matrix, initiation of radial tensile strength on fiber matrix interface takes place. That means the delamination is resulted. In other hand, if the Poisson's ratio of fiber is smaller than the Poisson's ratio of the matrix, initiation of peripheral tensile strength takes place. That means it develops matrix cracks. So, this is how the delamination and matrix cracks are justified. Fiber volume fraction is one of the most important parameter in textile structural composite manufacturing, which is defined as the area of the fiber divided by total area, surface area. Here in this case we call it total volume of the fiber in the total volume of the composite material. So, that means the volume of the fiber plus volume of the matrix constitute the total volume of the composite material. It is important to know how this fiber volume fraction is calculated. So, we have to assume some notations. Let us say the weight of the composite is W, fiber weight is Wf, matrix weight is Wm, fiber volume density is rho f, matrix volume density is rho m. Then you can calculate the fiber volume fraction by this formula. First you calculate the composite weight, it is the weight of the fiber plus weight of the matrix. Then you estimate the weight fraction of the fiber, capital Wf. Similarly, weight fraction of the matrix, capital Wm. Then you calculate fiber volume fraction, that is capital Vf, that is volume of the fiber, small vf, volume of the matrix, small vm. Then you can calculate the fiber volume fraction, that is capital Vf, by using this formula. In almost all textile structural composite, it is necessary to know what is the fiber volume fraction. We can compare the mechanical properties of a textile structural composite only when we can specify or we can predetermine what is the fiber volume fraction in the composite. Without knowing the fiber volume fraction in the composite, the mechanical properties of textile structural composite has no meaning. See in this slide how the fiber volume fraction and composite material is plotted here, the stress strain curve, the Vf critical. So, as you see, as we go on increasing the fiber volume in the composite material from critical stage to Vf is equal to 50%, Vf is equal to 90%, how the stress strain diagram of the composite material changes, that means modulus changes. So, this is just one example as far as tensile properties of composite material is concerned, how they how the fiber volume fraction influence these modulus. Similarly, all other mechanical properties can be studied with different fiber volume fraction in the structural composites.